So thank the organizer for inviting me to give a talk in this exciting workshop. My name is Huang. So I'm going to talk about some of my research towards human prosthesis symbiosis. So I lead a lab called Neuromuscular Rehabilitation Engineering Lab. What we're working on is we're working on human-machine system. In this system, the human and the man-made machine are not only physically attached with each other, but also we are hoping they'll function together seamlessly. So we call a human-machine symbiosis. So our goal is to merge human and wearable robots to improve quality of life for people who has physical disabilities. So in the lab, we work on a couple of projects. So first is showing you a neural-machine interface. We develop a neural control for artificial arms and legs. The group also using artificial intelligence in autonomous control, trying to make these wearable robots function coordinatedly with the human. Of course, before that, we need to understand how human-robot interact with each other and co-adapt. So in this talk, I will focus on our recent effort for developing optimal adaptive control of robotic lower limb prosthesis with the goal to provide personalized assistance for individual prosthesis user. Well, thank the organizer for posting this great picture on the website. This is a list of a beautiful robotic lower limb prosthesis developed from different groups. Compared to energetic passive device, because these robotic devices actually can power the joints, generate active motion and torque around the joints. So powered devices theoretically supposed to further improve the motor function, the walking function, and walking energetic efficiency for individual users. However, in a recent clinic, this benefit is not clearly shown. So we were wondering why this is the case. So I believe one of the explanations is this human device was not coordinated with each other well. So for most of the prosthetic device control, although it's trying to coordinate with the human's locomotion, but sometimes they just lose the coordinations with the human movement that are controlled by the human nervous system. Therefore, I believe that if we have a technology that allows the human device really coordinate seamlessly together, then this problem should be solved. We should see a clear benefit of this power device. So this slide shows a very typical way for current prosthesis control. In order to coordinate with a human, first the device needed to know the gait timing or gait phase. So in this case, we use a discrete gait phase, okay, using the formulate as a finite state machine. But you can also use a continuous gait variable as well. So then at a different gait timing, we will describe what's the desired knee mechanics in order to coordinate with the human. There are many controllers has been developed, but the general concept is very close. And then essentially the goal for the knee prosthesis is we wanted to generate knee kinematics during the gait that is very close to what we observe in able-bodied person. And also the desired knee mechanics here is also designed based upon the gait biomechanics that are observed in able-bodied person. However, for amputee, they have different motor deficits or weakness or different gait pattern developed. So they don't really, those parameters developed for able-bodied person may not necessarily fit for these people. It turns out that those parameters has to be adjusted in order to let this device better support, coordinate with the user. So in the clinic, how this control was adjusted is by the prosthetist So basically, it's manually toned and heuristically adjusted. So they use a software to adjust the control parameters a little at a time, and then until this procedure stop until the prosthesis sync, the gait looks fine. The challenge for this is one, this control, they can only adjust maybe 3 or 4 parameters, not all of them. And then also they could adjust usually 1 parameter at a time for human. And then therefore this coordination, so manually toned device to generate a coordination may not be that accurate. Because of that, I started to get really interested in designing this autonomous toning approach a couple of years ago. So my first approach is, how about we just develop artificial intelligence that is exactly mimicking what this human expert or prosthesist is actually doing. So we can observe what is their actions and then the patient's state, and then we can formulate this toning policy embedded in artificial intelligence. Then the adjustment of the control parameters could be automatically done. The challenge for that is really for the practical reason that find the expert, observe all the toning as well as, eliminate some of the bias. So therefore, it's quite challenging. It's possible. So my recent effort is collaborating with my colleague, Professor Jenny C. at Arizona State. So we designed another approach. It's also using a machine learning approach to tone the 12 control parameters simultaneously. So we use a reinforcement learning. So you can see in this structure, here is the human prosthesis system, so finite state impedance control. This part doesn't change. We designed the reinforcement learning as a supplementary control and then adjust these control parameters. So the input is we observe the state of a human prosthesis system, and then we provide actions, basically an adjustment of these control parameters. And then within this supplementary control is basically actor-critic reinforcement learning. We use the direct heuristic dynamic programming. The reason is it's model-free. We don't really need to have a physical model, a dynamic model of the human prosthesis system, which usually is very difficult to produce. So within this actor-critic, there's 2 neural networks. Here, the action network basically is the toning policy. So you see the state, and then you adjust the control parameter. And then the critic network is evaluate based on the current state and action, and then you evaluate and approximate the value function. Okay. So basically, this is optimal control. So our initial design of this reinforcement learning is based upon, with the goal to still generate this normative knee kinematics. And as you can see, here's the results. And then there's a control. The reinforcement learning toning is actually also a try and error heuristic adjustment of the control parameter until it approximate this desired kinematics. So in terms of walking, you can see these red dots is demonstrate the state, and initially it's quite far away from desired values. And then after toning, you can see that's meeting really well and approximate the curve well. So this slide shows our current update along this research line. Current efforts is trying to improve the reinforcement learning efficiency. The reason is we don't want a person walk really long until we can learn the policy. We want that this policy can be learned quickly. Instead of using actor-critic reinforcement learning, now we're building the reinforcement learning based upon the policy iteration framework. So how we can improve the learning efficiency is we could make use of offline data. So we can use the offline data. The algorithm allows to use the offline data to learn the initial policy rather than directly using the randomized policy. So in that sense, it will speed up the entire process. Another important thing I wanted to highlight is the robustness of the policy we have learned. So here shows the example. This is the learned policy from an able-bodied person walking with a device. And then we applied this to a patient who walk with the same device. And as you can see, within the forward phase, okay, the policy learned would be able to tone the control and then making the cost goes down really quick in a 3-gate phase. So there's no additional learning or update of the policy necessary. There's only 1-gate phase that the initial policy was not very stable. So therefore, additional policy update and learning is required. So there's 3 more updates until it came down to the finalized policy. So this is exciting because potentially we could also transfer some of the policy already learned to other people. That's another way we can improve the learning efficiency. So I also want to highlight reinforcement learning enabled us to conduct another research to investigate the influence of prosthesis control on gait symmetry. Quite often we got a question from people that are asking why not to including gait performance as your object function in reinforcement learning, such as metabolic cost. The problem is we don't even know if the prosthesis control or mechanics has an influence or has a relationship with these gait performance measures. Without knowing that, yes, we can design still including that into the control, but we don't know if it's successful. It's basically the design is blind. So therefore, we do need to know that knowledge first. However, for prosthesis control, in our case, we have 12 control parameters. Understanding these control on the gait performance is very difficult if we use a traditional biomechanics study design. However, we're excited because reinforcement learning, when we're using this toning, we actually check a lot of control combinations within the safety bound. And also, because reinforcement learning explore the control space quite efficiently. So therefore, it's actually giving us an opportunity to look how exactly these control parameters really influence the gait. So we started with the gait symmetry as the first study. So this plot shows the symmetry index that are calculated for the stance time symmetry. So if this index is 0, means perfect symmetry. The higher the value, the worse is the symmetry. And then for each individual subject, so we had to have tested 6 subjects. Each person, in average, everybody has walked with around 150 control combinations. And when we calculate, for each control, we calculate the gait symmetry index and put them together. As you can see, they cover a wide range. And this range is much larger than the variations when the person walking with the fixed control. So that means this distance, these variations, are really caused by the variation of the prosthesis mechanics. We also look at the biomechanics relationship that we find a strong correlations between the stance time symmetry and also net interlimb impulse. So the net interlimb impulse is calculated as a summation of the trailing propulsion impulse and the leading limb braking impulse. So if there's 2 impulse, 2 lag during the lag transition is well balanced, then we should be able to see a better stance time symmetry. Another interesting observation is we pick up the knee kinematics corresponding to each person's best symmetry index for the stance time. Although they are, they're different, and then some of them distance approximate, but not the same as the normative knee kinematics. But we all observe that for everybody, they have this stance time flexion. So I remember this is a debate at the beginning when we designed the control of prosthesis is, do we need this stance flexion because the patient don't like it? When they walk with this passive device, it's a fix, it's a locked joint. Actually, from this study, we see this bump might be necessary for improved gait symmetry. So here I want to summarize what I just said. So reinforcement learning is a very promising technology, being able to use to tone a high dimension prosthesis control simultaneously. And then it also enables us to understand the effects of a prosthesis control on gait performance. Based on our observation that the control do have a huge impact on gait symmetry. Therefore, potentially we could directly put the gait symmetry as an objective function into our reinforcement learning. So we are looking forward to work on this idea, and also balancing the intact side and the prosthetic side impulse for walking is critical to improve the gait temporal symmetry. So with that, I want to thank you for your attention, and then I'm ready for your question. Thanks.